Welcome students for the third lecture of photochemistry, and in this lecture we are going to discuss about the laws of photochemistry. Here, the photochemical reactions, they are governed with the help of four laws, and that four laws are as follows. The first law, it is Grotthuss-Draper law. Second law, it is Lambert's law. Third law, it is Beer's law. And the fourth law, it is the Stark-Einstein's law. And you are very well known that the first law of photochemistry, it is also called as the Grotthuss-Draper law. And according to the Grotthuss-Draper law, each and every photochemical reaction takes place by the absorption of radiation. And the Grotthuss-Draper law states that only those radiations are absorbed are effective in producing the photochemical change. And the significance of this law, it does not mean that all the absorbed radiations, they may cause a photochemical change. They may cause a photochemical change or may not. It depends on whether that the absorbing molecule or absorbing substance, whether it is photochemically active or inactive. And for this lecture, we are going to learn in detail the Lambert's law, Beer's law, and Stark-Einstein's law. We will see one by one these three laws and their mathematical expressions. Here, as already I have told you, when a beam of light falls on a solution or a homogeneous absorbing medium, a portion of light is absorbed within the medium, while the portion of light, it may be transmitted through the medium or it may be reflected from the absorbing medium. If I0 is the intensity of radiation falling on the medium, IA is the amount of radiation absorbed, intensity of amount of radiation absorbed, and IT is the amount of radiation transmitted. Then we can write the equation as the intensity of incident radiation. It is the sum of intensity of absorbed radiation plus intensity of transmitted radiation plus intensity of reflected radiation. And for glass liquid interface, the intensity of reflected radiation, it is very less, so it is not written here, and therefore we have the equation as I0, intensity of incident radiation, it is the sum of intensity of absorbed radiation plus intensity of transmitted radiation. And with the help of this equation, we can determine either IA, that means intensity of absorbed radiation, or intensity of transmitted radiation. Then the same thing, it is diagrammatically shown here. Suppose here, before entering into the absorbing medium, here we have the radiation with intensity I, that is the incident radiation, and here it is the absorbing medium in the form of here homogeneous form, and this is the transmitted light with intensity IT, absorbed light with intensity IA. In this diagram, I is the intensity of incident light, IA intensity of absorbed light, IT intensity of transmitted light. Simply remember these things, and here they have shown this B is the length or thickness of a sample. Then we will turn towards the statement of Lambert's law. Here the scientist Lambert, he investigated first how the intensity of incident light it decreases with the thickness of absorbing medium, and he formulated his investigation in the form of Lambert's law. The statement of Lambert's law, it is as follows. When a monochromatic radiation is passed through a solution, then the decrease in intensity of radiation with thickness of the solution is directly proportional to the intensity of incident light. Here, simply remember that when a monochromatic radiation passed through any homogeneous absorbing medium, the decrease in intensity of incident radiation, it decreases with the thickness of absorbing medium. Let we consider that I be the intensity of incident radiation and X be the thickness of the absorbing medium. Then mathematically the Lambert's law, it is written as here the intensity of incident radiation, it decreases with thickness. Therefore, we can say that this negative sign minus di by dx, it is proportional to I. This is the mathematical equation of Lambert's law. Mathematically, we can write minus di by dx, and here di by dx, it is the rate of change of intensity of incident radiation with thickness, and it decreases. So there is a negative sign, and it is proportional to the intensity. Here in this equation, di is a small decrease in intensity of light upon passing through a small distance x, a small distance dx, and I is the intensity of the monochromatic light just before entering the medium, as already I have shown in that diagram. And this is the mathematical expression of Lambert's law. Minus di by dx, that is the rate of decrease of intensity of incident radiation. It is proportional to the intensity. Then we can write this equation as minus di by dx, it is equal to this A into I, where this A, it is a proportionality constant. In your book they have given here K letter. You may use any letter, and remember that this A, it is a absorption coefficient. The proportionality constant, it is also called as the absorption coefficient. Again, here minus di by dx is the rate of decrease of intensity with thickness dx, and this A proportionality constant is called the absorption coefficient. Then rearranging this equation and integrating within proper limit, we get here, we rearrange this equation as di by I, it is equal to, this is a constant one, so we kept it out of the integration sign and the integration of dx. Here we can take and integrating this equation, that is integration of di by I, it is equal to this constant into integration of dx, and we get the integration as minus ln I, where this ln, it is the natural log to the log base e, and it is equal to proportionality constant, as it is the integration of dx, it is x plus c, where c, it is the constant of integration. And you know, when x, it is equal to 0, the intensity I, it is equal to I0. So c, it is equal to minus ln I0, and introducing this value of c in this equation number 3, and we rewrite again this equation as ln I divided by I0, it is equal to minus a into x, and this equation we may write in the form of exponential form. Here equation 4 we can also write I, it is equal to I0 into e raised to minus alpha into x, and these are the mathematical expressions of the Lambert's law. Then again we can write the equation number 5 as log I by I0, it is equal to minus a upon 2.303 into x, or log of I upon I0, it is equal to minus a dash into x, where a dash, it is equal to a upon 2.303, and this a dash is called as extinction. Okay, we will continue here. This a dash, it is equal to a upon 2.303, and it is called as extinction coefficient, and minus ln I by I0 is termed as absorbance of the medium. And remember that absorbance, it is also called as optical density, or optical density, it may be represented as capital A or capital D. Then the Lambert's law was extended by a scientist B.S., who showed that when the light passes through a solution of a given thickness, the fraction of incident light absorbed is dependent not only on intensity I of the light, but also on the concentration C of the solution, and this is known as the Beer's law. Here mathematically we can write the Beer's law equation as minus di by dx, it is proportional to concentration as well as thickness of the absorbing medium, and by combining the two laws we can write minus di by dx, it is proportional to I into C. or minus di by dx, it is equal to B into I into C. When the concentration C is expressed in moles per liter, then B is called as the molar absorption coefficient. Again, as in the case of Lambert's law equation, we may change that equation as log I by I0, it is equal to minus B in upon 2.303 into C into X, where this is the again second proportionality constant, and it is denoted by letter epsilon, and the value of epsilon, it is B, this B upon 2.303, and it is called as the molar extinction coefficient, which is expressed in mole liter per mole per centimeter. The molar extinction coefficient epsilon is dependent on the nature of absorbing substance as well as on the wavelength of incident light used, and this equation number 11 is commonly known as Beer's-Lambert's law. And you know, this law I by I0, it is nothing but the absorbance or optical density. That means for a solution having unit path length and unit concentration, its molar extinction coefficient, it becomes equal to the optical density or absorbance of the solution. Then we see the limitations of Lambert's-Beer's law. Here, the first limitation, it is that the electromagnetic radiation should be monochromatic. It should contain a single wavelength. The light beam should not be scattered, and solutions should be very dilute. Then and then the Lambert's-Beer's law is obeyed. Otherwise, it shows the deviations. Again, the mathematical part of Lambert's law we summarize here. You know, according to the mathematical expression of Lambert's law, the rate of change of intensity of incident light, it is proportional to the intensity. That means this negative sign, it is for the rate of change of intensity of incident light with the thickness, and it decreases. So we have written here negative sign, and here I have written this proportionality constant as K, as it is shown or as it is written in your book. So we can write minus di by dx, it is equal to K into I. Then rearranging this equation and integrating within proper limit, that means when x equal to 0, I equal to I0, and when x equal to 1, here I equal to I. And integration of this equation, it is equal to log of I0 by I, it is our absorbance. Remember, absorbance, it is the log of I0 upon I. The log value, it gives the absorbance. And this constant, proportionality constant or absorption coefficient upon 2.303, it gives the absorption coefficient, and depending on this absorbance, it is equal to absorption coefficient into thickness of the absorbing medium. Then basically we can write the Lambert's law in the exponential form as I, it is equal to I0 into e raised to minus alpha x and it is equal to I0 into 10 raised to minus kx. Therefore, k it is equal to alpha ln 10, and we can write I by I0 it is equal to e raised to minus alpha x, it is equal to 10 raised to minus kx, where k is a path length over which intensity is attenuated to 1/10, and therefore we can write I by I0 it is equal to 10 raised to minus kx. Then the Beer's law. When monochromatic radiation passes through solution, the decrease in intensity of radiation with thickness of solution is directly proportional to the intensity of incident light as well as the concentration of solution. That is the repetition here. Let I be the intensity of incident radiation and X be the thickness of the absorbing solution and C is the concentration. Then mathematically we can write the Beer's law as minus di by dx. It is proportional to concentration as well as the intensity of incident light. And we can write here minus di by dx. It is equal to k dash into C into I. Then rearranging this equation, here we take di by I and k dash C into dx, and integrating within proper limit we get ln I by I0, and it is equal to here k dash into C into L, and by changing the natural log we can write log to the base 10. So we multiply here for 2.303 log I0 by I, it is equal to k into C into L, and if we write this value as log I by I0, log of I0 by I, it is equal to k upon 2.303 into CL, where as already you know, log of I0 by I, it is the absorbance, and k upon 2.303 it is the molar extinction coefficient, and A it is the absorbance, and in case of Beer's law, absorbance it is equal to epsilon C into L. Here the ratio of I by I0 it is the transmittance, that means the fraction of incident light transmitted it is given by the transmittance, and T it is mathematically written as I by I0 or minus log T, it is equal to log of I0 I by I0, and it is the absorbance. From this equation it is seen that the absorbance of the solution is called as the optical density of a solution in a container of fixed path length, and it is directly proportional to the concentration of solution. Here this is the optical density, log of I0 by I, it is equal to epsilon, this is a Greek letter, then L it is a length of solution through which light passes, and C it is a concentration. This is the important equation, and this equation shows that there is a linear proportion in between optical density and concentration of the solution. The same equation is written here, and then the last point of the laws of photochemistry, that is the Stark Einstein's law. And you know that this law it is also called as the law of photochemical equivalence. The statement of this law, it states that each molecule absorbs a single photon of light in a primary process, and this law is also known as the law of photochemical equivalence as well as the principle of quantum activation. And this Stark-Einstein's law, it is explained as follows. Very simple one. Here we have A, it is our substance, and due to absorption of one photon, H nu, it becomes excited. That means enriched in energy. And the energy of single photon, it is given by H nu, where H, it is a Planck's constant, and nu, it is a frequency. Then the energy of one mole photon is called as Einstein energy, and the Einstein energy, it is given by N H nu, where N, it is the Avogadro number, again H, it is a Planck's constant, and nu, it is a frequency. And all of you know the frequency, it is nothing but the ratio of C by lambda. And when we put the values of N as 6.023 into 10 raised to 23 here, and the value of H as a 6.624 into 10 raised to minus 34 joule second, and the value of velocity of light as 3 into 10 raised to 8 meter second. Here there are some mistakes. Remember the value of N, Avogadro number, 10 raised to 23 here, 10 raised to 23, and the value of Planck's constant, 10 raised to minus 34 joules, and the value of velocity of light, 3 into 10 raised to 8 divided by lambda. And remember that here the value of lambda, it is in nanometer, and after solving this we get the energy per mole, and that energy is 11,096 to 0 divided by lambda. And remember that here lambda, it is in nanometers, and the unit of energy kilojoule per mole. So thank you. Next time we will see in a detail the quantum yield.